Hello and welcome to my video, lesson 5.3 on Compton scattering, or the Compton effect. Compton scattering is very similar to the photoelectric effect, except that the Compton scattering uses very thin metal foil, while the photoelectric effect uses thicker metal plates. And so here's the photoelectric effect. This is photoelectric. And basically what happens is a photon comes into a metal plate, coming in like that, in this direction, and it gets fully absorbed by an electron inside the metal plate. So there's an electron that's orbiting, a nucleus. That electron is fully absorbing the energy from the photon, and because it absorbs that energy, it gains extra kinetic energy. And if it gains enough, it's kind of like a planet leaving the orbit of the sun, or a spaceship leaving the orbit of a planet. It needs to have enough energy to have escape velocity, which we learn about in Physics 20. So the same sort of thing happens here. It needs to have enough energy that the electron can have an escape velocity from the orbit of the protons in the nucleus, because there's that electric force pulling it in. And so what happens is once it has enough energy, it launches out of the nucleus, and it shoots off that electron out to the side. And that's the photoelectric effect. That's from the last video. Now, what's different here is this is Compton scattering. So instead of a thick metal plate that absorbs the photon entirely, it's a very, very thin metal foil. And this thin metal foil has a bunch of electrons in a row, like this. And, they could be a couple atoms thick, but it's not like very, very thick. It's just a couple atoms thick. And it happens that the incident photon hits one of those electrons on one of those atoms. And because there's lots of room behind, it doesn't just absorb it, but it hits it and it imparts some momentum, kind of like the pool balls that we use in class. If two pool balls collide, like billiard balls, they'll fly off. This is momentum, like in the first unit in this course. And so the momentum is then conserved. It's an elastic collision, and the scattered photon is now more red than it was at the beginning. Okay, it has a longer wavelength, or a lower frequency, or less energy. All of those things mean the same thing. The electron is now flying off at a different angle, and this angle here and the angle above, they have to balance up the vertical and conserve the momentum in the horizontal. So that's essentially the Compton scattering effect. And here we can kind of see that as well with just kind of another nice diagram, coming in, going out. But the big difference is photoelectric effect is conserving energy only, and resulting in the discharge of an electron from the atom, and that's based off the work function of a given metal. And the Compton effect is the incoming photon colliding, not being absorbed, but colliding with an electron in the metal foil in an elastic collision, meaning conserving energy and momentum. So not just energy, but momentum as well. And so what we have is this sort of diagram, and we're like asking the question to ourselves, how can a photon with no mass have momentum when we know the formula for momentum from last unit looks like this: P equals mv. Well, the thing is, we can use E equals mc squared, the most famous of all physics formulas, to solve for the mass and remove mass from the equation. Because what this equation is saying is that energy is mass. Mass is energy, and we can go back and forth between the two. So with that in mind, we're going to rearrange this formula so it equals mass. So energy over c squared equals mass. And because of that, we can put that into the original equation. P equals, instead of m, I'm writing E over c squared times v. Now, before before we continue, that v is velocity. It stands for velocity. And if it's velocity of a photon, well, that's just c, speed of light. So this actually can be simplified to E over c. So momentum is energy over speed of light. Okay, so that's great. But let's talk about now the energy of a photon. The energy of a photon is given by this equation. So now what we can really do is we can, instead of writing energy, we're going to write hf over c. And so now momentum is Planck's constant, h, times frequency over speed of light, which is great. But we can also use this last equation and simplify a little bit by solving for well, f or c. It doesn't really matter. But if we solve for lambda, actually, it'll probably be very nice to see here. It'll be c over f. No, that's probably not the nicest way of looking at it. No, let's just plug that in instead of c. We'll do it that way. That's probably an easier way of looking at it. So hf over, and instead of c, we're writing lambda f. And so now we can see f and f cancel, so it's h over lambda. So that whole thing boils down to momentum is h over lambda. So this is the momentum of a photon. It doesn't need mass, it just needs a wavelength. And this is because of the equivalency. So this formula is really important to know about. This is in your formula sheet, so you don't need to memorize it, but that's where it came from. And all of those things are true about that formula. Okay, if you use conservation of energy and conservation of momentum, I'm not going to go through that. I don't think it would be a fun time. But if you did that, you would arrive at this equation here. This equation is the collision of a photon and an electron, where m down here at the bottom is the mass of an electron. Okay, the theta is the angle at which the photon is scattered, and the delta lambda is the change in wavelength. So remember that delta always means final minus initial. Alright, so let's do a couple example questions. If you can do them, I recommend you pause the video, try it out yourself, and see if you get the same answer that I do. But to determine the momentum of a photon is very simple. It's h over lambda. And so you can plug that in. And so the momentum is 1.00 times 10 to the negative 27. 1.00 times 10 to the negative 27. Now, because this is momentum, and we know momentum is mass times velocity, it's kilogram meters per second. Those are our units. Determine the wavelength of a photon with 3.2 times 10 to the 24 kilograms meters per second of momentum. So what we're seeing here is we're just reversing the equation. So we're going to basically flip it all around. So we just moved the p and the lambda over, and so now we can plug this in. So that's wavelength, and that would be in meters. If we wanted to convert that to something else, we certainly could. It would be 0.21 nanometers. Yep, that would be also correct. So either one of those is perfectly fine. So probably it's an X-ray. that might be a little bit strong. Whatever. We'll just, maybe that's, yeah, I don't know. That might be UV. A little bit less strong, I guess, the UV. Okay, so what is the initial wavelength of an X-ray which scatters at an angle of 35 degrees? So now we're going to use the delta lambda formula. So this is like this, and then it's H over MC 1 minus cos theta. And let me just double check that. Yep. So that's our formula that we have. It's in your formula sheet. It's just written as delta lambda instead, but it's the same thing. What we're looking for is the initial wavelength. So what we want to find is lambda I. So we're going to move that over, and we're going to move everything else over this way. So lambda F minus H over MC 1 minus cos theta equals lambda I. Okay, now we can plug all this into our calculator. So the initial wavelength was 1.2 times 10 to the negative 11 minus H is 6.63 times 10 to the exponent, negative 34 over MC. Okay, M is the mass of an electron. C is 3 times 10 to the 8, mass of an electron. Mass of an electron is 9.11 times 10 to the exponent negative 31. Then 1 minus cos of the angle, which is 35. And that should give us our answer. So it tells us that the initial wavelength was 1.156. Times 10 to the negative 11 meters. Let's just see. We've got 2 sig digs everywhere, so 1.2. Look at that. The initial and the final wavelength are essentially the same. There was very little difference, and that's because this angle was too small. The bigger the angle, the more of a scattering effect you will have. It shifted, but not by that much, right? Considering it was somewhere around there. 1.156. Right? It shifted, but not by very much. I wonder if there's any obvious amount. Yeah, there's not enough to say, not enough sig digs. If we just added sig digs, then it would work. I'm going to do that just for the purposes of making this question make any amount of sense. So what it would be 1/6. There you go, with 3 sig digs. We'll do that. It's much better this way. Okay, what is the angle at which a photon is scattered when the change in wavelength is this? And I'm going to just quickly fix that. There you go. What is the angle at which it is scattered? So considering this, and we know that the change in wavelength, so we actually know the delta lambda is that. So what we're going to do is we're going to start with this formula right here. Okay, and so at this point, we can move this over to the other side. So it's delta lambda MC over H, 1 minus cos theta. Now we need to solve for cos theta, which will be cos theta equals 1 minus, and then this whole delta lambda over mc over h. And then cos negative 1. So theta equals cos negative 1 of 1 minus delta lambda mc over h. We can plug all that into our calculator and we get... So what if we change this to be times 10 to the negative 13. There you go, that'll work. Okay, so what we can do, this is going to be kind of annoying, but I think we can get there, is we're gonna just change that. It's going to be cos negative 1 minus, so the formula is all still correct. I just clearly didn't do a good enough job making the question. It should have been times 10 to the negative 13. Okay, yeah, so if it's times 10 to the negative 13, then our answer would have been 37.4 degrees. Probably just 37 degrees is fine. Okay, let's just talk about example 5 for a moment. What is the greatest change in wavelength when a photon collides with an electron? Well, the biggest value that you could have is when cos theta is negative 1. Okay, so this would be the biggest value. Cos theta can be, just so we all know, just by itself, it can oscillate between negative 1, so this is greater than or less than, it's greater than or equal to negative 1, and it is less than or equal to positive 1. So it can oscillate between those, and if cos theta is negative 1, then the inside of that bracket becomes positive 2. When does that happen? Well, cos becomes a negative 1 when theta is 180. So basically, when the electron comes in, actually we'll go up to one of these examples here. So the theta is this angle here, right? The angle that it is scattering from the normal line, from where it would go otherwise. Now, if this angle is 180, that means it's going all the way around and scattering straight back where it came from. That is the most it can scatter, is going straight back. That means it's imparted the most amount of momentum. So that's what we're talking about here, 180 degrees. So with that in mind, we can rewrite that formula. So change in wavelength equals h over mc, 1 minus negative 1, which simplifies to two. And so just to write that out, it'd be 2h over mc, and that would be our final answer, the delta lambda. So the greatest change in wavelength is just by plugging all that in. So let's do that right now. 2 times h, which is 6.63 times 10 to the exponent negative 34, over mass, 9.11 times 10 to the exponent negative 31, I believe it is, kilograms, times speed of light, 3 times 10 to the exponent 8, so 4.85, times 10 to the negative 12. And so 3 sig digs because the letters or the values in there are 3 sig digs. Like the mass of an electron is 9.11, so that's 3 sig digs. And that's meters. So that would be our final answer, although you could certainly convert that to picometers. So 4.85 picometers also works. All right, I hope this video helps you better understand Compton scattering and the equations thereof. Good luck.